where there will be only phase change, temperature remaining constant for that particular refrigerating system. And there will be sensible heat rejection in the refrigerated system. Are you getting it now clear? One system is maintaining the temperature, there is phase change. So I will say latent heat absorption. And against what? Against sensible heat rejection. Now your thermodynamics course is over, your heat transfer course is over. So I hope you understand this very easily. Okay, so sensible heat rejection from a refrigerated system and latent heat absorption in a refrigerating system. Any doubt to anyone?
No, sir.
So most of the commercial refrigeration production units, systems, they work on the third principle, that is evaporation of a liquid. Because obvious reason, melting of the solid, the latent heat is very, very restricted, small amount. You take the example of water itself. It is 335 kJ per kg. Whereas for the evaporation of water, means boiling, then it will absorb 2257 kJ per kg. So more and more heat would be taken out. From what? From the refrigerated system. So even if I use 1 kg of ice, I will have only 335 kJ per kg latent heat. But if I use 1 liter of water, 1 kg of water is one and the same. Correct? Density is 1000. Then I can absorb 2257 kJ per kg. So 2257 in comparison with 335 is very, very large amount. So that is why generally preferred method is evaporation of liquid. And all such liquids are called as the refrigerants. Now I hope you are clear with refrigeration, refrigerated system, refrigerating system, and refrigerants. Any doubt to anyone?
No, sir.
Good. So if you observe the history of how this refrigeration came into existence and then further got developed, then we Indians should be very proud. We should feel very proud that we are the first people who were knowing about this technique of evaporative cooling. What is evaporative cooling? You are using it at your home in every summer. Give me the example. Very famous and common example. Look at the figure and tell me.
Sir, pot.
Earthen pot, correct. What happens? It's a porous stuff. You wrap some cloth which is dipped in water basically, and because of which the inside water gets cooled down. That is what is evaporative cooling. What is that particular process that I will cover in the air conditioning chapter, because it is very easy to understand from that perspective. But you have observed this right from your childhood days. Am I correct?
Yes, sir.
Yes, sir.
So होता क्या है शायद पता नहीं होगा, बट ऐसा कुछ होता है, इतना तो पता है. So we should feel proud that we are the first people, Egyptians and Indians, were the first people to know about this concept of evaporative cooling. This photo is somewhere near to Allahabad presently, where you can see that they are putting all those small vessels, earthen pots, inside some what I can say duct-like structure, and the top side there are holes, and the free air would be made to flow over them, and as such the evaporative cooling will be executed. And this happened somewhere like at least the known history, that is 2500 before Christ. It's a very, very old time. Since then Indian people were knowing about this particular science. But the unfortunate thing is that we could achieve the cooling but could not change the phase of the water. So ice was not known to us. Ice was known to the Chinese people around 1000 BC. Before that, Indian people or any other people in the world were not aware with the ice, like how to produce the ice. Ice was known, of course, but how to produce it, that was not known. The technique was not known. And you must be aware with the famous name Nero, the king of Rome. Rome was burning and he was playing the fiddle. Some funny story. He was the person, he was the king of the Roman Empire, and it was noted in the historical documents that he used to serve the cold beverages in his darbar. So he was knowing, or rather, the Roman people were knowing to serve how uh, I would not say ice, but how the beverages could be prepared or maintained. So uh, I would say that being the king, probably he could offer that, but at least those people were able to develop that particular technique with the help of which some cold drinks could be served. Then the next historical note could be taken directly after a long leap, 400 AD, and the East Indian people were knowing about the brine solution as well. What is the brine solution? Anybody knows?
10%
10% salt
NaCl.
and water.
Why we use that? Why we use that?
It is like an electrolyte, right?
No, no, from temperature perspective.
It
If you add,
reduces the
ah,
melting point.
correct, absolutely correct. गन्ने का जूस कभी पिया है? पिया तो सबने है. But why you add ice on that? Sorry, salt on the ice cubes, so that the melting point reduces, and you will feel even like colder comparative degree. Correct. If you add the ice in the गन्ने का juice, sugar cane, then you may achieve whatever, let's say 0 degrees Celsius. You put some salt on it. दिया होता है ना वहाँ पे छोटा डब्बी. So what is the purpose? That if you want still further lower temperature, then you should add the salt on the ice cube so that even the temperature further reduces and you will feel even colder. You had observed all these things. It's just like you're not aware why you are doing that. Correct?
Yes,
Yes,
sir.
sir.
So brine solution was known to East Indian people. East Indian means we people only, Asians, not West Indians. Okay. And the very first modern refrigeration note that was found in 1790, where two people, Thomas Harris and John Long, they were the first people to file a British patent about developing a refrigeration system. Refrigeration system. Okay. That was the first modern, what I can say, attempt. Then in 1834, this patent got converted into a practical machine. The patent was just like some theoretical thing. It was not developed. 1834, Perkins was the first person to develop a practical unit. And the refrigerant which he used at that time was simple ether. Okay. And you can observe it is a hand operated compressor. So naturally reciprocating one. It's a hand operated compressor. The diaphragm as shown in the figure. Can you see the cursor moving?
Yes, sir.
So this is like a diaphragm kind of thing when like a compression expansion. Okay. And then that gas will come over here, then through some leverages, then it goes to this coil structure and finally takes out the heat from this particular refrigerated system. Okay. It was a very crude. Expansion would take place somewhere in this section only. Okay. So this was the very first unit, very crude, very I would not say childish, but nowhere any sophistication, I mean to say. Okay. And then further people tried with different attempts to make it as sophisticated as possible. So 1834 Perkins, and then 1860 James Harrison, second person, who further exchanged the refrigerator, and instead of ether he used a typical one, sulfuric ether, because latent heat part. Ultimately he realized that the properties are the most important thing, so why to use one particular simple ether, why not to go for some acidic part. And basically what he achieved is a better performance. System remains same, only the performance improved. But because of that, with this particular change, he reported world's first installment. Earlier were all like prototypes. This was the first commercial unit, first installment of the refrigeration machine, refrigeration system. Then in 1851, parallelly, ये 1860 है, this is 1834. 1851, parallelly, one person came with the idea that why to use ether? Why any particular chemical? Why can't I use simple air which is abundantly and freely available? So name of this person is Dr. John Gorey, and this is a classical example where this doctor is not a PhD doctor, he is a medical doctor. And a medical doctor developed a engineering system. He wanted to perform the operations and some equipments to be maintained at the lower temperature so as to avoid the biological effects. So that is why he developed this particular unit. This is the schematic. This is the prototype which is still available in Royal Scientific Museum at London. If anyone of you happen to go over there for your MS or whatever higher studies, you can visit. It's still in working condition. So he was the first person to propose an idea that why we should use any chemical part as a refrigerant. Why not to use simple air? So obviously the drawback is that it will be always like a gas part. No phase change would be there. Correct? So my heat transfer would be simple MCP delta T. So whatever is the delta T, accordingly your performance, or vice versa. Whatever you want to achieve, accordingly there will be delta T. So we cannot extract the use of this latent heat part over here. But what I'm gaining about against that is that air freely available. So I can have any amount of mass as such of the air because वैसे freely available है. Whether you use any kind of chemical, then the mass will be restricted. But for air, you can develop the capacity of the unit can be anything because you can use 1 kg air, 10 kg air, 100 kg air. Nobody cares. So as I said, this is a classical example where a medical doctor developed an engineering unit. There is no other example in the history of engineering where a medical person helped. Other branches of engineering and science they developed, mathematicians helped, but this is the only example where a medical doctor developed an engineering unit. So as I had said, this is a restricted part as far as a very small heat transfer, because nowhere at no place the heat exchanges with the help of the phase change. Everything is sensible. So I need to go for MCP delta T. So either I can increase the mass and keep delta T small, or if the mass is small, then I have to increase the delta T. CP of air is constant, so I cannot change it. So that is the restriction, and because of the same, nowadays this is totally obsolete, except as I said, only the aircraft refrigeration. Please, again, I want you to take a note. Air refrigeration is a principle. Aircraft refrigeration is an application. I hope I'm clear.
Yes, sir.
Okay. So in aircraft application, we use the air refrigeration system. Okay. Moving further, 1861, Alexander Kirk was the first person to convert this air refrigeration system, not using air, but steam. Because he realized that if I use air, the properties are very, very poor. If I use steam, then at least I can enhance the performance. And he could produce 4 kg of ice by burning 1 kg of coal. Steam produce karna hai, so coal burning. So as such, I can calculate the COP afterwards. 4 kg of ice to latent heat and 1 kg of coal to calorific value. So I can get the COP. But he made it somewhat practical, as the air refrigeration was earlier a very huge bulky structure, because as I said, I need to go for either increase in mass or increase in delta T. So if I use the steam, then the size reduces and somewhat compact. And I would not say very compact. Nowadays, जैसा होता है वैसा नहीं, but little bit compact. So that made it more practical one. And in 1856, the revolutionary, what I can say, phenomenon or revolutionary concept came into reality, and that is the uh, chemical refrigerants instead of ether and all, like the conventional one. Now the chemical part. So Linde was the first person. Carl von Linde was the first person, Netherlands scientist, who developed a practical unit with the help of ammonia gas. So instead of ether and all air, like somewhat bulky structures, he could make the unit as compact as possible. Of course, we are taking the scale of reference as 1856, not 2022. And a revolutionary compact structure was developed by Linde. He started with the company named after his own name, like Linde Cryogenics, is still in existence in Netherlands. You can Google it if you want. He was the first person. Technique was same: reciprocating compressor, then evaporator, then heat rejection condenser, and etc. etc. But of a very uh, considerable, considerably reduced size. And with this, there was a boom, like why only ammonia? Then why not other gases? The ammonia is readily available, readily in the sense naturally available. So that is something started uh, getting developed. Then ammonia, then sulfur dioxide, and then so many other gases, which were known to the people at that time, of course, not chemical reaction, directly available. So in that sense, I am saying that it was a revolutionary move. This was the small unit which he developed at that time, 1856. You can see the gear mechanism for the rotation. Over here, bevel gears and the reciprocating compressors, huge compressors. Then the one first cylinder may be the condenser, second may be the evaporator. And a huge flywheel so as to drive that compressor part. So this was the first practical system. But of course, naturally COP was very low because of the ammonia properties, but at least it was a successful demonstration of the naturally available gases. Ammonia was naturally available at that time. You need not produce it separately. And this was the first commercial unit, ammonia refrigeration plant, reported by Linde. So now you can see this is the, what I can say, shaft of the compressor. This is a reciprocating unit. See the size of a person, one person standing at the top. This is the compressor part. And then all these are the condensers where the heat rejection would take place. So now you can see about the size of the huge unit. And still I'm saying that it was the smallest at that time. Earlier, like ether and air refrigeration units were even bigger than this. So this is how the science of refrigeration got, what I should say, started getting developed. That how to reduce the size and how to increase the performance. Because nobody cared at that time about the performance. The prime objective, sole intention is to produce the code. At what expense? I don't care. That was the attitude at that time. So such huge structure and COP is very, very small. But nobody cared at that time. So hereafter, after Linde's invention, Linde's system, people started thinking, why not to make this as compact as possible? Why not to increase the performance, COP, and etc. etc. So then further development. Then the next attempt, instead of ammonia, then use carbon dioxide, then sulfur dioxide, sulfur hexafluoride, SF6. You can use any gas you want based on the thermophysical properties. Your COP performance can be improved or degraded. Basic system remains same. there is a compressor, then this is the condenser, heat rejection, then through the valve there is expansion so that it will be at a lower pressure, lower temperature, and finally it will absorb the heat from the evaporator and comes back to complete the cycle. Okay. Now, till this point, there was only use of the steam engines. There was no other type of drive mechanism developed. No electrical invention were there at till that particular point. So the development was very slow because the compressor has to be run, rather had to be run by using the steam. What I mean to say, steam engine was the only option available, no other thing. But when the electric motors got invented, after that, this development got drastically changed because when you couple the electric motor to the compressor speed increases, and speed increases means your mass flow rate increases. Correct? So when I say per unit mass flow, m dot, then with the help of electric motors, let's say simple electric motor, so 1440 RPM. Whereas for the steam engine, the RPM were 200, 300, something like that. So naturally performance got like what I can say boost abruptly because of the invention of the electric motors. So this was the second attempt about drastic change in the performance. And the third attempt is in 1940s, where a French scientist Dupont, he invented the so-called CFCs, chlorofluorocarbon derivatives. So ethane, methane, propane, butane, heptane, whatever isopropyl compounds, etc., etc. Okay, and these were given the names as freons, chlorofluorocarbon derivatives. And because of these freons, there was no limitation. These are all chemical parts, chemical compounds, organic. Correct? 12 standard, organic chemistry. Alkane, alkene, alkynes. I hope you remember.
Yes, sir. Yes.
Lucky me. So these freons, including alkanes, alkenes, alkynes, all, even benzene compounds also, ring structure. So all these could be used successfully as the refrigerants and the performance got drastically improved because the thermophysical properties of the air or carbon dioxide or sulfur dioxide or ether are drastically on the lower side as compared to these chemical compounds, organic compounds. So if I use, let's say for example, ethane, okay, C2H6, then I can achieve even better performance because I can set the pressures in such a way that the latent heat of absorption from the liquid phase to the vapor phase would be considerably larger as compared to the conventional refrigerants, carbon dioxide and ammonia and all. So here the technique of vapor compression cycle started getting developed in true sense. So 1940s onwards, VCC, vapor compression cycle, got like the first choice of all the scientists. Because I already discussed that it is always better to go for the phase change. And these ethane, methane, propane, heptane, whatever. The boiling points are comparatively like close to the atmospheric one, not in very low levels like cryogenic range. So then why not to make use of that, absorb the latent heat, because latent heat is in per kg. So you add the mass and latent heat is very, very large. So mass is large, latent heat is large, m dot into HFG. Entire product is very large and that is what is the refrigeration effect. So the true sense development of vapor compression refrigeration cycle started after 1940s after the invention of the CFCs, chlorofluorocarbons. Okay. Unfortunately, nobody paid the attention towards the hazardous effects towards the environment. At that time, it was not even thought of also. वो सब बाद में आया. Okay. Now, another set of people started thinking in a way that what is the component which is responsible for the input parameter as far as the performance of the system is concerned, then output is refrigeration effect. What is the input? Compressor one. So what if I remove the compressor? Can I get rid of the compressor completely? The answer is no. Of course, you cannot take as a zero, because then your COP will be infinity. Refrigeration effect is a finite amount and compressor work is zero. Then your COP will be infinity, which is impossible, because you are not doing anything and you are receiving something. That is violation to the second law. We have seen this. Correct? So there will be compressor work. But how small I can keep it? So this another set of people started thinking, in instead of vapor compression, can I use some other technique? And they developed a vapor absorption system. Instead of vapor compression, it's a vapor absorption. So it's a simple physical phenomenon, nowhere any chemistry comes into picture. And it's a physical absorption. There are two phenomena. One is adsorption, ADSORB, other is ABSORB, absorption. What is the difference?
One is surface and one is volume.
Volume, exactly. So this is how the vapor absorption. So there will be some particular material which will absorb the vapor. So naturally pressure reduces. And then you heat it by some simple thermal technique. It will desorb that particular gas. And that will be, after the desorption, the pressure comes to the original condition. So this delta P will be very, very small. Absorption and desorption. But I need not have that compressor, right? And electrical energy and all such kind of things. So this is the advantage people try to harness as far as getting rid of the compressor part is concerned. The compressor nahi chahiye. What I basically want is a delta P. So why I should waste the electrical energy for that? Can I achieve it by some simple mechanical or any other physical technique? So the answers, one of the answer is the absorption. This is a simple physical absorption system. And this is the first unit developed by Ferdinand Carré, again a French scientist. French scientist contributed the most for refrigeration. I don't know the reason, but this is the fact. Dupont was French, Carré was French. Majority of people, even इसके बाद आप देखोगे, majority of the people contributed towards the development of refrigeration. They're French scientists. So the gas which he used, or rather I should say the pair which he used for the absorption and desorption, is ammonia and water. I hope you know that water is a great affinity for ammonia. So he made use of that. Expose karo water to the ammonia, it will absorb the ammonia, so natural pressure reduces. And then you just further heat the water, it will desorb it. So pressure comes back to the original condition. So this is how that delta P is created. And with the help of which I can further achieve the same performance as that of the vapor compression. But providing the thermal energy is a simple task. Providing the electrical energy naturally is a tedious task. Because electrical energy is a high grade energy, thermal energy is a low grade energy. Correct? So getting rid of the compressor part, in bracket electrical energy, was achieved by making use of the simple physical technique, that is absorption. There is adsorption refrigeration also. I have not included it over here because that is too complicated. The way it is vapor absorption, there is a vapor adsorption also. Okay. So, yes, ammonia vapor absorption system. It's a very simple technique was used for for this physical absorption, and whatever delta P achieved is responsible for the further refrigeration effect generated. Then he made it as a tandem way, that is either side, and that was a continuous vapor absorption system. Earlier it was like you have to give certain time for absorption, then you have to add the heat and then desorption and etc etc. He made some changes and made a circuit in which the gas flows continuously, and as such a continuous vapor absorption system was developed. So this is just like the extension of the earlier one. Okay, and this is our regular discontinuous. So at certain time there will be absorption, certain time there will be desorption. It would not be a continuous one. Third set of people, they started thinking in a way that why I should even use any gas, not even air. Air refrigeration bhi nahi chahiye, no chemical is required. Are there any other techniques through which I can achieve the refrigeration? So Peltier was another scientist, again French. I guess you are aware with Peltier effect or not? Seebeck effect
No,
and
sir.
Peltier effect. Seebeck effect and Peltier effect are reverse of each other. So here it is said that if you pass the electric current through a typical material, okay, semiconductor material, not all, certain. If you pass the current, then one side of the semiconductor material would be like at the lower temperature side and the other at the higher temperature side. And that is what is shown through this animation. I hope you are able to see the animation or not.
Yes, yes.
It is moving now, yes. So on the lower side, if I expose that lower temperature side to some particular component, or rather, sorry, compartment, then it would be the refrigerated system. And the same heat would be passed through that semiconductor and will get rejected at the top. So this is how the refrigeration system got developed, and a refrigerated space, let's say, at the bottom will have the cooling effect. So there are certain materials available in the world which, if you connect like in an electric circuit, see here, positive and negative. So this is connected this way. They are not connected directly over here. So this is negative ions, this is positive ions. Okay, so if I connect the set of semiconducting materials in a typical circuit, electrical circuit, then I can generate a delta T, temperature differential across both the surfaces. Now this is a physical phenomenon. So no compressor required, no nothing, no phase change, no refrigerant itself. Rather, I would say the semiconductor material can be called as a refrigerant. You change the semiconductor material, naturally the rate of heat transfer would be altered. Okay, so electron flow and the hole flow. ये तो आपको समझ में आता होगा ना फर्स्ट ईयर फिजिक्स.
Yes, sir.
So this is the Peltier effect, and the Seebeck effect is exactly reverse. Seebeck proved that if you expose the material one at the higher side and one at the lower side, then the current starts flowing. Peltier said you pass the current, you will get the temperature differential. Seebeck said you create the temperature differential, current starts flowing in the circuit. So exactly reverse. I thought you would be aware with Seebeck effect and Peltier effect, maybe in mechatronics course or something like that, or as a general knowledge, whatever, fine. So this concept or this system, I should say, refrigeration system, was developed by the same person. Peltier invented this way, so that is why the name was Peltier effect. And then he proved that if the temperature differential can be created, you can use it for your refrigeration purpose. Okay. Now, further part, yeah, this is another way of what I can say, depicting the system. So here there is an electric battery, charge, positive, negative, and the holes and electron movement, p type and n type. So there is a heat absorption, there is a heat rejection. Okay, the way you connect, accordingly, the side will be changed. If you pass the current clockwise or anti-clockwise, positive, negative, accordingly, top surface either will be absorbing the heat or rejecting the heat, doesn't matter. Ultimately the same. One will act as a hole carrier and the other as an electron carrier. Now people started thinking in a way that how I can improve the performance. Fine, COP, or which other materials I can use. And another set of people, they started thinking in a way that what is the lowest possible temperature to be achieved in the world. Because the objective of people were completely different. Few people were interested in enhancing the performance. Few people were interested in getting rid of the electrical part. Few people were interested in reducing the size. Few people were interested in finding out what is the lowest possible temperature. Okay, refrigeration is developed, but what is the lowest temperature that I can achieve? So that branch came into existence at 1877, and we call it as cryogenics now. So I'm giving you just like some glimpses of how this refrigeration took these people in further lowest possible achievable temperature. So Raoul Pictet was another, again, French scientist who liquefied the oxygen first. Till this particular time, 1877, it was universally declared that no gases, natural gases, could be liquefied. And they were called as the permanent gases. So oxygen, nitrogen, argon, krypton, xenon, hydrogen, helium, all such gases were declared to be permanent gases. They can never be liquefied. Solidification to chhodi do, not even liquefaction possible. But then Pictet developed a system in such a way that the oxygen could be liquefied. And this was a photo of the liquid oxygen, what he achieved at that time. And the system which he used to liquefy the oxygen. In 1877, it was the first successful attempt of liquefaction of the permanent gases, so-called permanent gases. And then again, there was a boom that if oxygen could be liquefied, then why not nitrogen? Why not hydrogen? And likewise. So the similar systems like this got developed by many people, and then accordingly, all the gases were liquefied. So oxygen, उसके बाद nitrogen, उसके बाद argon, krypton, xenon, chlorine. Chlorine तो बहुत पहले ही हो गया, but all such kind of so-called natural gases, and then declared to be permanent gases, all got liquefied. Now the question came how to store them, because the temperature was very, very low. So if it gets exposed to the atmosphere immediately, then the liquid gets immediately converted into the vapor form, again gas. So how to store? Let's say liquid nitrogen. How to store? So Sir James Dewar, a British scientist, came with the idea very similar to a thermos flask. And we call this by his name itself as a Dewar Flask. James Dewar ke naam se Dewar Flask. So Dewar Flask is a specialized type of insulation used inside this particular thermos, where you can store the cryogenic liquids for a longer time. The reason being, when you reach to such lower temperatures, the material properties drastically change. You cannot use liquid nitrogen in your simple stainless steel household vessel. It will immediately get cracked down. So that is the reason special material, or special way, I should say, got developed to store them properly. Okay. So this is that Dewar vessel. You can see it over here. It's very similar to a thermos flask, but the way it gets manufactured and assembled is slightly different. And you can see over here liquid nitrogen getting shifted to this container, Dewar flask, and then it can be moved anywhere you want. So this person is taking out liquid nitrogen and storing it inside the flask. This is a very old one version, very crude. This is the latest one. sophisticated. And 1908 was the last gas liquefied, that is helium. Its temperature is 4.2 Kelvin, that is minus 269 degrees Celsius. That was the last gas. Oxygen around 90 Kelvin, nitrogen 77 Kelvin, hydrogen 20 Kelvin, and argon, krypton, xenon all are above 54, neon 54 Kelvin, 87 Kelvin, etc. etc. The last gas remaining was helium, and that got liquefied by a scientist from Netherlands, Kamerlin Onnes. He liquefied the helium gas at 4.2 K. This is the setup which he developed, and this is the person. But with this liquefaction existence, beautiful discovery, and that is what is called as superconductivity. I hope you have at least heard the name superconductivity.
Yes, sir.
So that came into existence in 1908 with the help of the liquefaction of helium. The helium is the, what I can say, most naughty and funniest gas towards the liquefaction. It changes the properties drastically and unbelievably. So there were two phenomena came into reality. One is the superconductivity, the second is the superfluidity. The superconductivity, what is that? This is the lab where commonly known as achieved 4.2 K liquefaction point. And what is superconductivity? You can see over here resistance, electrical resistance is a function of temperature. Everybody knows that. So as the temperature reduces, resistance also reduces, fine. But at a certain temperature, this resistance becomes practically zero. You can see it is even lesser than 10 raised to minus 5 ohms, 0.00005, oh, sorry, 1. 10 raised to minus 5, and even lesser than that. So we call it a practically zero. And then what happens is the resistance becomes zero, so it becomes a superconductor. Correct? V upon I. Resistance value. R is 0. The current is infinity. V is 0. And that is what we call it as a superconductor. And there are hundreds of applications nowadays by using this superconducting material. The most famous is the maglev train, magnetically levitated train. That is why we call it as a maglev train. So what happens over there in reality is that you pass the, let's say, liquid helium through the rail. At the normal situation, the coach, I can say, bogie, whatever you call it, is like a normal thing. It is resting on the rail. But you pass the liquid helium through the rail, उससे क्या होगा? It becomes a superconductive. Okay, it becomes the magnetic also. Okay, it's not just superconducting, it becomes a magnetic also. There are some magnets attached at the bottom of the bogie or the coach. So the rail becomes magnetic, and there is another magnet at the bottom of the coach. So opposite same poles repel each other, opposite attract each other. So they repel, and the whole bogie gets lifted, hawa mein. And then you give a small amount of power, it starts moving. So this is practically a contactless drive, no wheel required. Surface contact chhodi do, wheel is a point contact, but not even that required. So whatever is the resistance of the air, atmospheric air, that is the only thing remaining. Otherwise, it is a practically frictionless drive. And that is possible to achieve nowadays so very easily. That is what is the maglev train. See, if your frictional resistance is reduced, your size will be drastically large, higher side. Anyone aware of the highest speed achieved by any maglev train? General knowledge.
No, sir. No, sir.
Japanese magnet.
Huh?
So Japanese magnet.
No, not
600.
Japanese. Not Japanese. It's a Chinese one. Shanghai International Airport. The maglev train over there has achieved 635 kilometer per hour. Shanghai International Airport to any other city. 635 kilometers per hour speed. Because now you can imagine that it is a completely frictionless drive, no wheel. You can imagine that two surfaces resting on each other. ठीक है, एक लकड़े पे दूसरा लकड़ा एक रखा हुआ है, फॉर एग्जाम्पल, एंड यू पास द हीलियम, लिक्विड हीलियम थ्रू नीचे का लकड़ा, which becomes a magnetic part now, superconductivity, so magnetic, and the same magnets attached at the bottom of the bogie, so naturally they repel each other, so the entire bogie gets lifted in air, and then you give a drive. No friction, no contact itself. So like practically I can say some highest speed, theoretically infinite. So this is how the maglev train works. I will try to show you some video about this maybe in the next lecture. Okay. With the help of, no, sorry. This is superconductivity. The another effect which I have not covered over here is the superfluidity. There are two isotopes of helium, helium-4 and helium-3. I hope you are aware with this. Hydrogen के भी दो है, hydrogen and deuterium. Similarly, helium also has two isotopes, molecular weight 4 and molecular weight 3. Are you aware or not?
Yes, sir. Yes, sir.
So helium-3 becomes like a superfluid. Helium-4 is not a superfluid. Helium-3 is superfluid. And what is the meaning of superfluidity? Superfluidity means your inertial resistance becomes zero. जैसे यहाँ पे electrical resistance becomes zero, we call it superconductivity. We know from fluid mechanics, every fluid has inertial resistance, correct, during the flow. That is why it remains at some particular shape. Say for example, glass में water भर के रखा हुआ है. Then the inertial resistance. So this inertial resistance becomes zero. And what will happen if the inertial resistance for any fluid becomes zero? Then it is free to move anywhere it wants. So practically what happens is that, let's say if you pour helium, liquid helium in a glass and try to reduce the temperature below 3.2 K, liquid helium, not liquid helium, helium. Helium has two isotopes. One is helium-4, helium-3. So helium-4 liquefaction point is 4.2 K. And helium-3 liquefaction point is 3.2 K. So if you reduce the temperature below 3.2 K, then the helium liquid starts climbing the walls of the glass on its own, and then it moves away. अपने आप पानी नहीं बोल सकते, whatever, liquid helium अपने आप ग्लास की वॉल चढ़ेगा और बाहर उतर के निकल जाएगा. This happens practically. I am doubtful whether you are able to imagine this or not, but this happens practically. Very difficult to imagine, no? एक ग्लास में पानी रखा हुआ है, पानी अपने आप सरफेस ऊपर चढ़ रहा है, ग्लास सरफेस, और बाहर आके निकल गया, टेबल पे निकल गया. It is happening like on its own. Bhoot. But this happens in reality. Your inertial resistance forces become zero. That is what is called as superfluidity. So both the superconductivity and superfluidity came into reality after the liquefaction of helium. Had anyone seen any such video? I will try to find out the video. superfluidity. I have seen this practically in IIT Bombay, but unfortunately no video was taken at that time. Otherwise, I could have shown you. Let's see if something available on the internet. But just imagine that there is a water bottle filled with water, and the temperature reduces. Water starts climbing the bottle wall, plastic wall, and then comes out of the bottle and then goes away somewhere on that table on which the bottle is kept. This happens practically. That is what is superconductivity. Okay. Now the last technique towards achieving the lowest possible temperature. Cryogenic shuru ho gaya. Now we reach to liquefaction of oxygen, that is 90 Kelvin. Then helium 4.2 Kelvin. The question is 4.2 K or whatever, helium 3 liya to 3.2 K. Is the last temperature practically achievable? Answer is no. We can go as close as possible to absolute zero. Second law of thermodynamics says that absolute zero is impossible. Fine, impossible. But we can reach as close as possible to that. I'm not saying equal to zero, but very close to zero. That is possible. And this last technique is called as the adiabatic demagnetization. And this was developed in 1926 by two scientists, Gayak and Peter Debye, sometimes called a Debye principle also. So this is very similar to your vapor compression system. So here, this is, let's say, vapor compression system. What happens over here is that, let's say, this is some refrigerant. Okay, you compress it, apply pressure. Can you see this?
Yes, sir.
Then fine. Okay, so you apply the pressure plus P. Gas is compressed. Refrigerant is compressed. So T plus delta T, higher temperature because of compression, correct? Then you reject the heat. We call this as condenser. Heat reject ho gaya. So it comes back to original temperature T. Then you reduce the pressure, expansion. Because of the expansion, further temperature reduction, T minus delta T. Correct? And then you absorb the heat, which is my refrigeration effect. Yahan pe refrigerated space hai from which it will take the heat, plus Q. Correct? And then it comes back to the original T and completes the cycle. So compression, that is compressor, heat rejection, that is condenser, expansion, that is throttle, and then heat addition, which is evaporator. These are the four prime parts of a vapor compression cycle. Of course, we are going to deal with this in much more depth in that particular chapter, but this is the basic principle. Same is applicable over here in the magnetic refrigeration, called as the adiabatic demagnetization. So hota kya hai, the magnetic dipoles in any of the material are always randomly oriented. You add some heat, add the magnetization, add the magnetic effect. You bring it in contact with some magnet. Then these dipoles get oriented. They are random. Now they are oriented in some manner. And because of that, the temperature increases. Okay, then you reject the heat. Usse kya hoga? Magnet is as it is there. You are just rejecting the heat. So dipoles are still arranged, but the temperature is reduced because of the heat rejection. Okay, then you remove the magnetic field. So usse kya hoga? Again, this gets randomly oriented. And because of this movement of the dipoles in randomly oriented manner, the temperature further reduces. Ye delta T higher tha, you reject the heat, it comes to the original T, and then you remove the magnet part also. So further temperature reduction. And these randomly oriented dipoles, now you add the heat. This is my refrigeration effect, as same as here. And it comes to the original temperature. This is the lower temperature. This is the original temperature, which completes the cycle again. So here you are adding the magnetic field, here you are rejecting the magnetic field. So that is why it is a magnetization and demagnetization. And how do you achieve it? Adiabatic way. Because when you add the magnetic field, There is a possibility that heat rejection may take place, so you have to execute it in the adiabatic way. Then and then only there will be increase in temperature. Otherwise, the whole effect will be wasted. You add the magnetic part and reject the temperature. क्या होगा? कुछ नहीं. T का T ही रहेगा. I want T plus delta T. So for that, it has to be executed both, adding the magnetic field and removing the magnetic field. Both processes, magnetization and demagnetization, both processes should be executed in the adiabatic way. So that is why the name adiabatic demagnetization, because my refrigeration effect is executed at the demagnetization part. जब ये निकल जाएगा तब होगा. That is why demagnetization. So with the help of this technique, we can reach as close as possible to the absolute 0 Kelvin scale. Anybody is aware with what is the minimum temperature till date reported in the world? Google it.
Sir, nano Kelvin.
हाँ कितना?
10⁻⁹ Kelvin.
वो नैनो की डेफिनेशन है. नैनो केल्विन में कितना? व्हाट इज द मैग्नीट्यूड? 1 नैनो केल्विन, 100 नैनो केल्विन.
1 sir.
1 nano Kelvin.
Yes sir.
Where is this reference? Who achieved it?
एक वीडियो में देखा था वो.
YouTube video.
Yes sir, they were experimenting something.
वो तो मैं कोई भी वीडियो बना के डाल दूंगा. What is authenticity?
वो ब्रिटिश ब्रॉडकास्टिंग कंपनी का था एक्सपेरिमेंट सब.
The BBC na. So BBC
Yes.
has made it as a proposed one. The practical value of the minimum temperature till date achieved in the world is 35 nano Kelvin, greater than absolute zero. Absolute zero is, let's say, minus 273.15 degrees Celsius. So plus 35 nano Kelvin. That is the minimum temperature achieved till date. And that had taken place in that CERN project, Hadron. Because everywhere there is a superconductivity thing employed. So magnetization and demagnetization very easy for them. So in that CERN project, we achieved 35 nano Kelvin, greater than absolute zero. Okay, just a piece of information. And this technique of magnetization and demagnetization takes place in such a small tube. So now you imagine the development from this bulky structure to this much compact structure. This is what is the scientific research or the development, what you call it, R&D. Okay, and we reach from, let's say, minus or let's say 0 degrees Celsius, ice formation, 0 degrees Celsius to almost minus 273.15. This is what is a R&D. Okay, here is another interpretation, entropy versus temperature. थोड़ा सा उल्टा chart है. What you are quite aware is the T and S chart. This is S versus T chart. Nothing wrong in that, na? I just exchange the or interchange the axis. Instead of TS chart, I'm saying ST chart. So here you can say magnetization, demagnetization, etc., etc. No magnetic field, this is the, with magnetic field, this is the value. Fine. These are randomly oriented, shown over here, and these are nicely oriented. Very less random orientation is there. Baki sab properly oriented. So this is how I achieved about the isothermal part and the isentropic part. And this will make you remember about which cycle? Second year thermodynamics. Isothermal and isentropic.
Carnot.
Carnot cycle. Exactly correct. So this makes Carnot cycle practically possible. Isn't it interesting? फ्लूइड
Yes, sir.
अपने आप बहते जाता है, बॉटल की वॉल चढ़ के फ्लूइड बाहर आ जाता है. Practical Carnot cycle is possible. Very, very interesting. Okay, CR, how much time left?
Extra time आहे सर.
Eh?
झाला 10, 12, 20 झाले.
अरे बापरे. Oh, sorry. Because after this, I would be starting with this ice trade, which is another important, interesting thing that I will cover in the next lecture. Do we have tomorrow any lecture? No, no.
No, sir.
Okay. But tomorrow I will be traveling, but there is no loss for you people as such. Okay, fine. And today we will be finalizing with your lab part, okay? Kainar sir and myself. Fine. Any doubt to anyone up to this part? Or should we end the meet?
We can end the class.
Okay, fine. Chalo, thank you.
Thank you, sir. Thank you, sir. Bye.
Thank you, sir.
Thank you, sir.
Thank you.